Okay, I think it's time I will start today's lecture. So first, I will be talking about introduction to soft robotics. And at the beginning, in the last lecture, I didn't introduce myself because I do have introduction slide in this presentation file. So I will use this opportunity to introduce myself. So my name is Po-Ting Ling. I got my a PhD degree from Rutgers. It's in USA, Rutgers University. So I got my PhD in 2010. My research was actually about optimization when I was a PhD student. So it's a mathematical research, statistical research, nothing practical. So I sit in front of the computer and then write computer codes. After I finished postdoc in Rutgers, I went back to Taiwan. My first job was in Zhongyuan Christian University. I was an assistant professor in Zhongyuan, and I realized in Taiwan, you have to work on practical research to get funding. If you only focus on theories, it's difficult to get funding. So I started to apply optimization in many different fields, including robotics. So one of my research field is robotics. And I think my experience in the past 10 years or more than 10 years should be able to show you something interesting about robotics. So in 2017, I was promoted to Taiwan Tech. So this is already my 6th year of working in Taiwan Tech. So just this year, I became the director of Center for Intelligent Robotics. So I will be focusing more about robotics in the following years. So in the past 11 years, from 2012 to this year, I have been involved in 99 projects. I'm not sure which one is my 100th project. So I got many research fundings. Some are small, some are big, but work on many different things. Publish some papers. And as you can see, I publish a lot more international conference papers than journal because I enjoy present my research work somewhere outside of Taiwan. That's why I publish a lot of international conference papers. I do have some inventions in the past few years, 16 of them. Recently, I got an Excellence Research Award from Taiwan Tech. I got the Young Robotics Researcher Award in 2021, Young Investigator in 2018. And even earlier, I got some competition awards. Anyway, that's pretty much about myself. I want to now move on to soft robotics. If you check Wikipedia, soft robotics is a kind of robot that use compliant materials. What does compliant mean? Compliant means soft. Okay, so instead of rigid links, they use compliant links. But why don't they just use soft? Because sometimes it's not exactly soft. For example, if you have a snake robot, maybe the body itself is rigid, but it's compliant. It's moving very flexibly, and it can, for example, go through into pipes. Then we sometimes consider them as soft robotics as well. Okay, so soft doesn't mean it has to be soft. Sometimes it's a little rigid, but usually soft robotics are quite flexible. And one important thing is, why do we use soft robots? Usually when we use rigid robots, it's strong, the body is rigid. When you have contact with the traditional robot, it's dangerous. For example, if a robot hit this desk, the desk can be damaged, or the motor of the robot can be damaged. However, if you have a softer skin or softer motion, maybe it's safer. So one important thing for soft robotics is that they want to improve the safety. So they want to introduce compliance into robot, softness into robots. Or you can say they want the robots to behave more like men, more like human, or more like some kind of animal, okay? Now, let me share this interesting slide with you. Hold on. How do I switch this up? Okay, help me. So this picture, this figure was taken from a journal paper down over here. In my presentation file, I put the reference for whatever I use in the presentation. In my homework assignment, I will ask you to maybe study for some papers. You can also study the papers I cite over here. Okay. Okay, anyway, my TA is helping me to, make the upper toolbar disappear. Anyway, in this particular figure, what does it mean? It's the it's the development trend of soft robots. You can see in very early, in 1950, there are very, very little research papers about soft robots. Very little. But nowadays, every year, we have more than 1,000 research papers about soft robots. Actually, this is a trend of robots, okay? And soft robots is getting more, okay? Of course, in the future, after 2020, this trend can be converging, reaching some stable development, or it could drop. We don't know. But at this point, 2023, soft robotics is still a very hot research topic in robotics. So that's why in this year's development, we want to teach our students, try to build some kind of soft robots, okay? They need to see it. hi, 面板。Yes. Okay. Thank you. So in my next slide, hold on. There's actually a journal called Soft Robotics being created several years ago in 2015. This is the first year this journal has been created. So maybe you guys don't know, but I will share with you what does impact factor mean. So soft robotics is one of the top journal article or journal magazine in robotics. When you have an impact factor of 8.9, that means every article in this journal will be cited more than 7.9 times per year. Okay, so over here you can see the highest of soft robot reach around more than 8. It was very high, and you can see the ranking of this journal was #1. #1 robotics journal from 2015 to 2017. This is telling you how hot this research topic was. Even up to this year, although the ranking dropped a little bit, right now is ranking #6. This is because some other robotics journal was created in the past few years. You can see in 2015, there were only 25 robotics journal in the world. Now we have 30. So that means 5 more journals were created, and they were having higher impact factor than soft robotics. So there are 5 more different journals are hotter than soft robotics. However, this is still very popular journal. So if later on you want to find some good ideas about soft robotics, I put the journal webpage over here. You can go to this webpage to find some articles about soft robotics. Okay, now this is something I collected from the articles I read, and something I based on my experience. So in soft robotics, there are certain things, certain factors you can think about when you want to work on this research. What kind of material you are going to use? So over here, I mentioned 4 different kinds of material. PDMS is a polymer. EcoFlex is a polymer. Silicon rubber, also a kind of polymer. 3D printed materials, also polymers. So mostly for soft robotics, researchers are using polymers to build the body of soft robots, not metal or not wood or paper. They use polymers. That's why in our following lecture, we want to request the Japanese professor to introduce the characteristics of polymers. And also we want to study the strength of polymers, because polymers are very popular for making soft robots. Design concept. Okay, in this soft robot, sometimes you want the body of the robot to be weak, or sometimes you want the body to be strong. Where do you want to have weaker body? Where do you want to have softer body? Usually, when you have, for example, if I want to make a soft robot just like my arm, like a human arm. Human arm can bend somewhere at the joint. So if I build a soft robot like a human arm, and I want this robot arm to bend somewhere, this joint area should be softer. And over here, this link from over here to the elbow, I don't want to bend this part of my human arm. So if I want this part to be stronger without bending, I can use stronger materials. So sometimes we have composite materials. Some part of the soft robot is weaker, some other parts are stronger. So that's why over here I mentioned composite. Composite means a mixture of different kinds of materials. And this is Japanese, origami. What does origami mean? Origami means you want to fold papers. So paper folding is a kind of research direction as well. In research, we directly use the Japanese word origami. Origami is actually about paper folding. So in some of the example I show later, they are using origami structure. Okay, methods to manufacture. Molding is one way. Molding is like you have a container, you pour polymer into the container, cure the polymer, take the polymer out. That's called molding. If you want to use the molding technique, you need to design the mold. Okay, in many of the following examples, they use molding. Soft lithography. Soft lithography is a kind of micro fabrication process. It's in semiconductor, they usually build structures layer by layer. But for semiconductor, the materials are hard materials. It's usually used for computer chips. They learn that kind of layer structure idea to soft robotics. So that's why they call this soft lithography. It's a layer creation procedure, but the material is soft, okay? Soft lithography. And also 3D printing is also popular inside the manufacturing procedure. Applications, what do we usually make? How do we usually use soft robotics for? Sometimes we use it to make a soft gripper or robotic legs, actuator. So maybe it's like a snake body that can move like a snake, or to sensor. When you have contact, you want to understand there's contact, or some kind of valve, turn on or turn off something, or some other biomedical applications. And over here, since we want to move the soft robot or deform the soft robot, we use the word actuate. We want to actuate the movement. And there are some popular ways to actuate. One is to use pressure, use air. Pneumatic means use high pressure air to pump the device and it will deform its shape. So pneumatic is use air. Cable driven is like you put a cable inside, you pull the cable, okay? And sometimes they directly have motors inside this soft robot. And since we are using soft lithography or multiple layers of molds, between layers, sometimes you need to worry about how to bond them together, bonding. So in my following example, we even use plasma bonding because we want to glue 2 layers of PDMS together. But PDMS is a kind of material that's quite unique. Its surface energy is too low. So when you put 2 polymers together with low surface energy, it doesn't create bonding. So plasma will activate the surface energy of PDMS. Then when you put them together, they will create some kind of covalent bond. Okay, so I will show some example later on. Okay, models. So when you build a soft robot, you want to know how to control it. You want to know if you pump gas into the robot, how much deformation is going to generate. Because if you don't understand the relationship between deformation and actuation, you cannot control it. Or how much force you can generate. Okay, and for the actuation, usually there are many different kinds. Linear motion, bending, or twisting, okay? In your pipe robot, maybe you can have linear motion or bending like a worm, or maybe some kind of twisting, I don't know. you can try to think of some good ideas to generate different kinds of motion. And for control, what is kinematics? Kinematics means the theory about motion. Okay, what is forward and backward? Forward kinematics is the mathematics to describe some system's motion. And by how much control you have, kinematics will tell you how much movement it will have. But how about backward kinematics? Backward means, actually it should be reverse kinematics. If you want to have some kind of motion, then how much control you need to make. So usually forward kinematics is having some kind of control and generate motion. Backward or reverse is the study for understanding how much control you need to generate some kind of motion. Okay, so this map will help you to understand what you need to think about for soft robotics. Okay. Next, different materials for actuation. Over here, PVDF is a very unique material. It's a piezoelectric material. What is piezoelectric? This kind of material will generate electricity if you apply force. When it deforms, it will generate electricity. Reversely, if you apply electricity to the material, it will deform. So for soft robots, PVDF sometimes is utilized as actuators. So you can use electricity to control the deformation of the material. So PZT is also piezoelectric. This is also piezoelectric. And there are some other kind of materials, carbon nanotube, shape memory alloy, and so on. Shape memory polymer. When you study some papers about soft robotics, you will see those kind of materials being used. And you can tell from this table, it's telling you the materials toward this direction actually are softer because it generates more deformation. And along this direction is stronger. Okay, it requires, it can generate more force. Okay, so using this map, you can try to understand how each material behave differently from each other. Okay. Now, in today's presentation, mostly we will use cable-driven and pneumatic. So here are two examples about cable-driven and pneumatic. This is cable-driven. So for example, if you have a soft robot and you have 3 cables and you have 3 motors, by pulling the cables, the length of the cable changes. So as you can imagine, this cable was shortened by pulling. So this soft robot bent toward right. So probably this soft robot's motion can be controlled by these 3 motors. Just decide how much rotation you have to generate how much pulling force you have, then how much deformation you can create. Over here is another example where you have different channels, different regions, like air chambers. And this is about pumping pressure into each channel. And you have valve over here. You can turn on the valve or increase the pressure. By changing the pressure inside each channel, the chamber deforms. using those deformations, this soft robot change its shape. Okay. So in my student's demonstration, he used pressure, but you don't really need to use pressure. You can use cable if you like cable. In my following slide, I will show you both kind of examples. Okay. Now, soft robots actually has a lot of applications, and it really depends on what kind of application you need. Then you need to define what kind of performance this robot have. So like in this table, it's telling you, sometimes you want the soft robot to bring something to the worker. This is like inside a factory, and you have soft robots carrying something. So over here, you need a stronger soft robot, but this motion can be very slow. It doesn't happen all the time. So the frequency of movement, every hour, the number of picks is very small. But over here at the middle, this is like a soft robot to deliver products, like a mail room or in a factory. So maybe in this application, it requires more frequent movement. The number of picks per hour increases. Since it's moving more frequently, maybe it's harder to have stronger design. So you can see the domain drops to this area. And there are some other soft robots are in this area where the strength of a robot is not very strong. However, it works with human. It's like guiding a human. So for example, this person is always carrying something. It's bending his body, carrying something. So those are soft skeleton. We call the exoskeleton surrounding your human body can generate some force, help you to carry some loads. If you are using this kind of soft robot for as a human body pressure supporting structure, usually the frequency of the motion is very high, but you don't really need to have too much force. So it really depends on what kind of application you are working on. The design, the idea is different, and maybe this there are some key factor needs to be changed. Okay. Now another table over here also separate different applications into this matrix. So what does this matrix mean? If you go up toward the table, it's actually telling you the soft robot application behaves more like a human or some kind of species in biology. So over here you can see at the bottom, this is like a human assisting device, maybe just helping the old people or some kind of guiding device. This doesn't look like a human. But up to here, a robot arm or a glove or some kind of a palm-shaped soft robot looks more like a biological structure. Okay, so going up, you have you design the geometry more like a live animal or a person. Going toward right, you design something that is more compatible with human species or animals or mostly with human. So over here, like going right, you want soft robot to deliver drugs. The mechanism doesn't look like an animal, but it's highly compatible with human body. You want the robot to be able to go into your body and deliver drugs. Okay, so for each domain, your design concept needs to change. For example, if you want to have high human body compatibility, maybe the material has to be specially prepared. You cannot use dirty materials. You need to have very clean, biocompatible materials. Or if you want to have a very biomimicking motions, then maybe the structure has to be creatively designed so it moves like a human. So this also a guidance for you to understand how researchers divide different design concepts into this matrix. Okay, and there's another way to think about software robotics with different applications. That way is to understand its stiffness. Sometimes you can have a soft robot, actually it's not so soft. It's that the body could be stiff. Or you can have a soft robot that is completely soft. This Octobot is completely made by PDMS. It's like a jelly-like. And the actuation inside is by the channel inside each leg. And usually, inside its head, there are some chemical reaction to generate pressure gas. The gas going into the chamber of the leg and then deform the Octobot's leg. So this is completely soft. However, this one on the other side of the domain, you can see this looks like a dog mimicking robot with actually rigid legs. However, even the material that was used for the dog's leg is rigid, but because of the shape, it still has some flexibility. So this kind of doggy robot can be jumpy or walking just like a dog. Okay, so from here in this domain of soft robotics, you can see almost every robot, you can say it's compliant, but not always soft. The structure here is rigid, but it's flexible. Okay, so I think the good word from Wikipedia is compliant. Okay, so in your own design, think about how stiff your robot should be. And that probably will help you to make a final decision. Okay, now let's talk about some examples. So here's a wearable soft robot. Okay, over here, there are 3 different kinds of soft robot. They are, you wear them in different parts of your body. The first one is a cable-driven soft exosuit. So there are motors inside and generate some kind of pulling force. So if you, for example, if you are a soldier, you are fighting a war on the field. This kind of suit can help you to have better strength. Maybe you can jump higher or run faster because those cable can generate more force or can help you to carry loads. Second one is also cable driven, but completely different application. It's for the glove, okay? And the third one is also for the glove. This is a human arm, but over here you can see it's not a human finger. It's like a pipe. This is actually the pneumatic pipe. So they pump gas into those exo fingers so that it will bend. it helps you to bend your fingers. So you can have an even stronger grip, okay? So when human workers is trying to carry something, those Exo gloves can help you to generate more force. Maybe it's easier for you to carry a heavier object. Okay, so soft robots, those are also called soft robots. Okay, I think this one looks more like a robot. So this is a very general manufacturing procedure for pneumatic robot. Many researchers just follow this way. Usually they have a mold. And in this example, I think you can use a 3D printer to print the mold. And they have some structure for piping inside the mold. And then you pour some kind of polymer into the mold. After curing, you can take out the material. Because of that piping structure inside the mold, you have a channel being generated inside the soft material. All you need to do next is to cover. You need a cover, right? You have one piece and then you have some grooves for channels, but it's open channel. You need to close the channel. So usually you need a second layer bound with the first layer, just like this. You have a top layer and a bottom layer. So you then have a closed channel inside. Then you can pump air into the channel to form a bubble. Then the bonding strength between two layers become very important. If the bonding strength is weak, when you pump gas into the channel, it will explode, right? So for different materials, they have different ways to bond. In my TA's example, they are using silicon rubber. So for silicon rubber, it's very easy to bond. For example, if you have two pieces of silicon rubber, how to bond them? You can apply a little more silicon rubber on one side and then attach them. So you have liquid silicon rubber between two layers. And then you just cure the silicon rubber at the middle, then it's bonded. Okay, so for silicon rubber, it's easy. But for some examples I will show later on, PDMS is not easy to bond. Okay, so in this particular example over here, you can see it's very interesting. When they blow the bubble, the deformation between the top edge and the bottom edge is different. Because the top layer is thicker, bottom layer is thinner. So bottom layer is weaker. When it's generating a bubble, the bottom layer will form a bigger bubble. So you can see this bigger bubble was formed at the bottom side. The top side is having a smaller bubble. So if you have something like this, it doesn't generate motion. It just blow a bubble. It has no motion. However, if you do another thing, if you apply a piece of paper at the bottom layer, because paper doesn't stretch. So when they blow the bubble, the paper remains its same size. It doesn't stretch. So this layer of the paper limit the deformation of the bottom layer. So what will happen is all the deformation goes to the upper side. So it's actually forming a really unique shape like this. It bends a lot. So same material, but just one more layer of piece of paper generate this kind of bending. So if you want to have a bending motion, you can blow a bubble in the soft robot. But if you didn't create the layer properly, you just have an expanding arm, but it doesn't bend. So it's very, sometimes you need some creative idea to try how to bend a soft robot. Sometimes it's not easy. In my experience, sometimes you build a structure with different parameters. You want the robot to bend this way, but actually in the end, it bends the other way. It's very, very unstable or not easy to predict, unpredictable, okay? So in the following slides, I hope those examples will help you to have a sense of soft robotics design in your mind. So later on, when you do your project, you know what to do, okay? So this is origami design. So paper fold, learn from paper folding. They fold this kind of structure in this way. Why do they do that? They want this arm to have some kind of flexibility. Okay, so when this arm have contact with an object, it doesn't break the wall and the body doesn't break. Okay, so over here, what you see in this area, this is actually silicon rubber. But how do you have silicon rubber in this shape? They create a mold for the silicon rubber right here. So you need to design the mold in a very unique way so it becomes a origami design. Okay, this is silicon rubber actually. And at the middle part, they call this a bendable joint. This is also silicon rubber, but they create this in a different shape. It's not origami anymore. And they will blow air to this so-called bellows area or the bendable joints. When this kind of shape has high pressure, it behaves like a spring. It will elongate, become longer. I will show you in the next slide. From here, you can see the bendable joint parts has different amount of pressure, and the one on the very left become longest. And then the one on the right doesn't lengthen too much. Because of the combination of those bendable joints at the end, the entire arm bend and move to certain direction and position. So in this research area, people would like to know how much pressure control in each channel can generate what kind of movement. So, and usually the relationship is nonlinear. From this figure, you can tell this is the amount of pressure being applied, and this is how much angle being generated. It's not like usually in soft robotics, nothing is linear relationship. Usually everything is nonlinear relationship. That's why nowadays people spend a lot of time on soft robotics because it's very challenging. Okay. This is how they integrate the whole thing. Okay. They have the soft robots right here. They want to use a camera to visualize the movement. So they have a camera. And over here, they have some kind of mechatronic system to control the pressure. They have different pipes of the air channel. They use valves to decide which channel turns on and off. They use computer to tell the valve how to turn on and off. So usually for a soft robotic system, you not only need to build something like this, you also need to figure out how to control it. So I think this is a very good research area where mechanical engineers and material engineers can work together. Okay. So let's move on. This example is very related to what you want to do. Okay, this is a worm robot. It's a biomimicking robot. It actually moves like a worm. Okay, learn from the real world. Learn from the real animal. So from here you can tell this kind of worm actually has a small legs at the front part of his body and the very last part of his body. There's no legs at the middle. So how does the worm usually move? It doesn't move like us. We move by taking motions of our legs. But what worms move is not by the legs. Their legs are so short. If they are walking like human, their walking speed will be so slow, right? So what they do is they use their flexible, bendable body. They change the shape of his body to have a bigger movement. Okay, that's why in this research, they try to make the middle part of the body weaker and more flexible. They generate some kind of structure right here to allow flexible movements. And in the front and the end, they have magnets, magnetic nanopowders inside the front and back area. So later on, they can use magnet to control the movement of the front and the back. And the whole thing was made by 3D printing. This is the photo curable 3D printing. So they have some kind of resin. They have some light to solidify the resin to generate a shape like this. And when they generate the front and back, they mix magnetic nanopowders inside. So the way they deform the worm is to have magnets. Just move the magnets, okay? So that the body part bends. So why do they want to make this? They want to deliver drugs inside human body. This is not yet a real application, but this is the research idea. For example, you want to deliver drugs to your lung. I think this is your lung, right? And maybe you can swallow the worm robot. The worm robot goes to, no, you don't swallow. It goes from your nose, I guess, and then goes into the area closer to your lung and then deliver drugs. Okay. So how can you move the robot inside your body? Because the structure has magnetic nanoparticle. If you have a strong magnetic field, maybe you can control how the worm moves inside your body. That's the idea. Okay, but from this research paper, you can tell you sometimes want to learn from the real world, the biological animals. Okay, you want to learn from real animal bodies. And I hope we can see some interesting biomimicking robots at the end of your project. Okay, here's another example. This robot has 4 legs. It's not actuated by magnetic. It's actuated by air. Pneumatic soft robot with 4 legs. So how was this made? Same trick. They have multiple layers of structures. In some of the layers, they generate the air channels, like this, air channel. And then they will pump air into the channel. So for this particular case, you can see they have 5 different channels. So on the right hand side, you can tell when they do not put air into the channel, they use red color to represent no pressure. Green color means pressure. So you can see those two legs were pressurized. So these two legs bend. Then the body bends as well, and the whole body bends. Then the two legs in the back release the gas, but now bend the front legs. Then release the body. Finally, release the two front legs. And from the first picture to the last one, you can tell it moved a little bit, right? So it's like, it's moving like this, okay? So I think some kind of animal probably moves like this, but very small movement, very small. Can you design this in a different way so it moves faster? Yeah, maybe you can, right? So in our project, you can actually make something like this if you design well. You can actually do this. You can have this kind of motion. Okay, we will have some kind of competition to see which robot crawls faster. Okay, we'll see. Okay, starting from this
Excuse me,
slide.
sir.
Yes, sorry.
Yeah, it's the classroom view is not shown anymore. Can you fix that?
Say again, sorry.
The classroom view, like on the Nokia S41.
What do you mean?
Okay, it fixed right now. Thank you. Yeah.
Oh, it's fixed. Okay.
Okay, I'm sorry.
So TA, can you help me? What do I do right now? Share? Yeah, just help me. Okay. Oh, I think we only have 9 more minutes for this morning. So from this particular slide, moving on, all the slides I have for the rest of the presentation are the presentation slides from myself and my students. So I will start to share what I have done and also what my students have done. You can tell from here, this is actually my master thesis, Po-Ting Ling master thesis, 2007. So I have done this 16 years ago, right? So this is actually what I did when I was in Rutgers. So at the moment, I was using the material called PDMS. The full name is polydimethylsiloxane. That's a full name. But I'm not a chemical engineer, so I don't really know how it looks like from the inside. I just know the name. Okay, it's called PDMS. So PDMS usually it's a mixture of two liquid, like a jelly-like liquid. And the ratio is 10 to 1. If you have different ratio, it becomes softer or harder. Usually, I follow the construction, use 10 to 1. So it looks like a glue. And when you mix together and wait for hours, it will solidify and become elastomer. So what I did was I follow the idea of soft lithography. I have some kind of mold, and then I want to generate a channel inside this PDMS. So I need to grow. When I create a mold, I need some structure to represent the channel, and then I pour PDMS on top. Then I cure. This is like heating. So after curing, I can take it away. I take away this PDMS. Okay. And later on the right-hand side, I want to bond them together to form a channel. So on the right-hand side, actually what happened was you can use plasma bonding. The trick is called plasma bonding, and it's actually oxygen plasma. When you apply oxygen plasma onto PDMS, it will bombard the surface of the PDMS and generate all those OH at the surface of PDMS. And those OH will be there temporary because it's an unstable state of its surface. You need to put two PDMS together quickly, otherwise those OH will disappear. When you wait for a few seconds later, it will disappear. So it's a very unstable state after oxygen plasma, maybe only 10 seconds to operate. But if you have a good skill of operating, you can put those two together, and from the picture you can realize, because I have a channel on the upper structure, it has no contact with the bottom. So only the face-to-face area has bonding, and you will generate some kind of covalent bond. It's like an O bond, and there is one oxygen, water will be evaporated because you have OH. So if one H2O goes out, the remaining part is O, and that O will be forcing a O bond. O bond is a very strong bonding, right? Covalent bond. So the plasma bonding is actually very strong. And what's inside the channel has no bonding. So it actually forms a closed area. That's how you can pump air into the channel without leaking. And many researchers use this trick to generate channels. So let me show you some examples. And because we want to understand how strong the bonding was, so when I was a master student, I need to build a force model. I need to generate some kind of a device. I want to blow air onto this bubble. I want to break it. I want to know how much pressure is needed to break this bubble. So by this force model, I can then study the bonding force. This F at the end is the bonding force. So I'm not going to spend too much time on this because you don't need to do this. But in this kind of research, the bonding force, the amount of bonding force is important. You need to know if your bonding technique can generate good bonding. Okay, I'm just going to go through this because this morning's lecture is almost done. Just to let you know how I generate that kind of a bonding structure. So this is actually a fancy slide. I built multiple structures in parallel and then put them together. First, I have a Petri dish for PDMS. So when I have a PDMS right here, I use a needle to punch a hole. Okay, so this is a PDMS structure with a through hole. Over here, I will generate a very thin layer of PDMS. I use spin coating. And for the thin layer, I will use some structure, also PDMS, only attach onto the membrane, not bonding, just attach, just to cover some part of the membrane. And then everything goes into oxygen plasma. Then I will take away this yellow structure. As you can see, because of this yellow structure, some part of the membrane was not exposed underneath plasma. So there's an area on the membrane has no plasma treatment. So when you put these two together, because in this area, one side has no treatment for plasma it doesn't generate OH structure. So it doesn't generate bonding at the center. So that actually helps us to have zero bonding at the middle. If I blow air from this hole, this area forms a bubble. So this is a very interesting research. I can show you some videos. So this is the bubble. I need to play the video. Hold on. I want to jump out of the slide so I can play the video, but I need to share, right? I need to share this one. Okay. Because the video was not playing. I need to play right here. So it's a research about popping the bubbles. Okay, over here you can tell I'm pumping air pressure into it, and it's forming a very thin a bubble with very thin thickness. It's a membrane, and it's about to expand and then about to explode. So I use image processing to study the diameter of the bubble. And then it pops. It was a screen capture. So over here, you can tell when you apply on this figure, the diameter of the bubble doesn't change too much when the pressure was not high. So I keep on increasing the pressure until it reaches certain point where I see in this particular case, for example, 12 psi. The diameter of the bubble starts to increase until it breaks. So I call this critical pressure. This is where the bonding between two layers start to lose its ability to bond. So I think this pressure is important. So in that force model I did earlier, I use critical pressure and critical diameter to study the force. So first I have a theoretical model. I built a device to measure some key parameters. Then I can estimate the bonding force. Okay, so that was what I have done. If I know the bonding force in the future, I can tell if I design a channel, I know how much pressure I can apply to any design. Okay, so I think this is the first part of my presentation. And in the following section in the afternoon, I will continue from here. Okay. Before I stop, is there any questions from the audience? How do I should stop this. Okay, any questions from the audience? I hope the first lecture is interesting for you. If you miss anything, the presentation file is online. Okay. So any questions from the students? Okay, so if there's no questions, I think this is already lunchtime from Japan. So I will give the Japanese participants some time to have lunch. For our Taiwanese students, you have 2 hours to take a break. We will start again at 1 p.m. Okay, so thank you for morning section. See you at 1 p.m. Okay, bye-bye.